The ship is moving. It's heaving up and down with every single ocean swell, even while it's holding its position perfectly on DP. But 3,000 meters below, that drill bit, it needs to stay at a perfectly constant depth. It has to apply constant weight on bit, almost as if the vessel weren't moving at all. So how exactly do we solve that massive contradiction? Well, it comes down to 6 massive electric motors constantly adjusting line speed in real time. We're talking about the active heave drawworks, or AHD.
It really is the ultimate deep water paradox. You've got this massive ship violently rising and falling on the surface, but thousands of meters down at the seabed, the reality has to be completely different. The drill bit must remain perfectly still. If we didn't have a way to compensate for that surface movement, every single wave would translate directly down the pipe. The drill string would just be bouncing up and down at the bit, causing wildly inconsistent weight, destroying the equipment, and basically making drilling completely impossible.
So, to solve this major offshore physics problem, we have to look at the active heave.
If you look right in the center of the derrick, you'll find the AHD. Basically, it's the rig's main hoisting system, the massive winch used for running drill string and equipment into the well. But it's been upgraded with an active heave motor control. What this means in plain language is that as the ship rises on a wave, the Drawworks pays out cable at the exact same rate to keep the string at the same depth. And then, as the ship falls, it reels it right back in. The drum is just constantly chasing the vessel's motion in real time.
And the precision here is honestly mind-blowing. Because of this system, they're able to maintain the weight within an incredibly tight range. We're talking only a few hundred pounds of difference applied at the bit. Think about that for a second. You have thousands of feet of heavy steel pipe hanging in the ocean, the ship is pitching in the waves, and yet the actual weight pressing down on the rock barely fluctuates at all. That's exactly what keeps the bit from smashing into the formation.
But pulling off that level of precision takes serious muscle. Let's look at the power behind the pull and how this solution scales up.
Now, a modern drill ship like the GF-12000 is a dual derrick ship, so it actually relies on 2 completely independent Drawworks systems working side by side. For the main well, they use an AHD 1250-9000 system, which is rated to lift a massive 1,250 short tons. Then you've got the auxiliary well running an AHD 1000-6900 system, rated for 1,000 short tons. Suspending that much steel in the water column and constantly adjusting it multiple times a second, that requires an unbelievable amount of power.
Just how much power? Try 9,000 total horsepower. That staggering number is what's driving just the main well's active heave system.
And if we break down the math here, it's pretty straightforward. You take the number of motors and multiply it by the horsepower per motor to get your total installed drive power. For the main, well, that 9,000 horsepower doesn't just come from one giant motor. It comes from 6 separate 1,500 horsepower GE liquid-cooled AC motors. The auxiliary system follows the exact same logic, using 5 1,150 horsepower AC motors to reach its 5,750 total horsepower. Splitting the power up like this is a very deliberate, absolutely crucial architectural choice.
It all comes down to a concept called graceful degradation. By using an array of smaller motors instead of one massive one, you get the incredibly fine responsiveness you need for smooth, continuous micro-adjustments rather than jerky, aggressive steps. But more importantly, it provides redundancy. If you lose one of those 6 motors on the main Drawworks, the capacity reduces safely. The system degrades gracefully, meaning you still have 7,500 horsepower to secure the load rather than catastrophically failing and dropping the drill string.
Okay, to really visualize these real-time control systems in action, I love using the angler analogy.
Think about an angler standing on a small, rocking boat. They're trying to keep their fishing lure at a perfectly steady depth underwater. Every time the boat pitches up or down, their hand instinctively adjusts the line, right? The active heave Drawworks is exactly that same instinct, just completely automated. The thing most people miss is that AHD isn't just a heavy-duty winch. It's a highly advanced control system reacting many times per second. It's functionally similar to the active suspension in a high-end car, just applied to a vertical drill string instead of a chassis, and scaled up to handle 1,250 short tons of steel.
But here's the catch. All that mechanical muscle is totally blind without instant data, which brings us to the very real danger of digital delays and sensor lag. The system uses real-time vessel motion data from the ship's MRU sensors, the same ones feeding the DP system, to calculate its next move. So we have to ask ourselves, what happens if those motion sensors report the vessel's heave with just a half-second delay? Half a second might sound like nothing.
But in a system reacting multiple times per second, half a second is an eternity. If there's a lag, the Drawworks reacts to where the ship was, not where it is. It creates a completely out-of-phase reaction. So right when the ship is rising naturally, the Drawworks might pull up instead of paying out, causing massive dynamic load spikes. Or it might feed line out right as the ship is falling, suddenly slamming the bit down into the rock. This is a known cause of severe drill string damage. It just goes to show that the real-time sensor software cannot just be trusted blindly. It has to be monitored continuously.
Now, what goes up must eventually slow down. Think about all that motor power used for hoisting. It also has to absorb the massive kinetic energy required to stop 1,250 tons of steel from moving downward. You don't just clamp a standard friction brake on that kind of weight. Instead, the Drawworks uses its motors in reverse, feeding into incredible regenerative braking systems. But we'll actually be diving deep into that specific control system in our next explainer.
So, I'll leave you with this thought today. If we've successfully automated the exact physics needed to suspend 1,250 tons of steel perfectly still above the seabed, right in the middle of a violently moving ocean, what other offshore engineering impossibilities are being solved out there right now? It really makes you wonder what else is possible on the open ocean.